Hi everybody, welcome to our workshop. Today we're going to be talking about a tutorial that highlights the features of the NRF-Shield. We're going to be making two nodes that can talk to each other. The sender node sends data to the receiver, which then displays it on an LCD. The NRF-Shield is a very useful and flexible shield that can be added to many different types of Arduinos. The common ones, the Arduino Uno R3, the Mega, the Leonardo, the Due. There's many types that are similar that this shield is compatible with. And the key feature of this shield is that it adds RF communications to your project very easily with a lot of flexibility. So in today's tutorial, we're going to be talking about how to set this up, how to configure it. We're going to be going over the hardware aspect as well as the software, with the note that the software aspect will keep fairly simple as possible. There's a lot of nuance with RF communication. Really, the details are in the scripting part. So, and that's been done. There's a lot of information with the RF communications modules that we'll be using. So we're going to keep that fairly brief. That being said, we will publish all of the script that we're using for this tutorial. So we're going to cover hardware and software, have an actual example. But before we can get into the details of that, let us get into the highlights of the features of the NRF-Shield and what it can do for your project. The first feature and the most obvious feature to discuss is, well, what kind of RF modules are we actually talking about here? And it is actually the very popular, very common NRF-24L01 Plus. This is likely the chip that you have seen before and used before. This is the NRF-24L01 Plus standard size. There's three versions I will be discussing, and just so I don't break my tongue, I'm going to be referring to all of these as simply NRF or NRF modules. This is the standard one, and you can see that the breakout in the back is a 2x4 pin breakout, okay, with a standard pitch of 2.54 millimeters. So likely you have come across this before if you're watching this video now. You have likely also come across this one. This one has the long antenna. This is the NRF-24L01 Plus PA plus LNA. Again, I'm referring to all of these as simply NRF modules. So this one has a much larger footprint. It has a large antenna. It will require more power to transmit. It has the same breakout over here, the 2x4, but you can see there's two extra pins here. These are grounded pins. Typically, they do not get included when you purchase this module, wherever you purchase it from. So I encourage just put a 1x1 pin, a male header, right, just a standard one, put them in at this as well. We'll be discussing that later when we talk about assembling the nodes. You might have not come across this one. This package is the mini package. Same functionality as the standard one, it's just a smaller footprint. You can see the breakout in this case is a 1x8. So not a 2x4, or 1x8, and the pitch is not the standard 2.54, rather it is half of that. This is the smaller footprint of that. So feature number one of the NRF-Shield is that it can interface all three of these. So if you look at the board itself, you can see labeled here NRF interface, referring to all three of those NRF modules I just discussed. You can see everything is labeled here with the pinouts. This is the 2x4, this is the 1x8, and here we've got a space for not the 1x1 pin that is grounded, but actually it's a 1x2. So again, this one doesn't typically have the 1x1 added. You have to add it. I haven't seen it before it added, but this is a 1x1, but this interface has space for a 1x2. The second one will not be used. Why is that done? Because a 1x2 female header that goes into here is much more stable than if you were to use a 1x1. So for stability, for adding the module in a rigid manner, we suggest to use a 1x2 here. So you can see the interface includes all three of these. And it should go without saying that the user should only use one module at a time. So you could technically plug in the large footprint and the mini at the same time. They do fit. We don't recommend that at all. That being said, let's move on to feature number two. The second feature we're going to discuss is the hardware selection pin that the user can select on the NRF-Shield itself. This adds a lot of flexibility both in terms of the script, which we'll see later in this tutorial, but also in terms of how to actually power the NRF modules. Taking a closer look at these hardware selection pins, you might notice a row of pins right here. These are grouped into threes, with the first selection being the VCC pin, the next the CSN pin, then the CE pin, and finally the interrupt pin. If you look closely, you might see that there is an unplated, unmarked through hole in between each of these four groups of three. That is added for soldering convenience. Instead of soldering 1x3 pin male header here and here and here and here, which is cumbersome and difficult to keep straight and aligned, so it won't look as good, it is a lot easier to solder a single 1x15 pin male header across. You can take a standard male header, 40 pin male header like this, and break it at 15 points. We will link a video in the description where we show how to break male and female headers. When you do so, you get this, a 15 pin male header. Take the short end and you can put it right in like that. Now these holes in the middle, they're not electrically connected, so when you solder the 3 here, the 3 here, the 3 here, and the 3 here at the bottom, afterwards you can simply pull out these pins with a pair of pliers. Then you're left with 3, 3, 3, 3, and one long black connecting piece here. For example, we have done this in this module here. This module we'll discuss in a little bit. I mean to say node actually. In this node I will discuss a little bit, but you can see here that we've done exactly the same thing. We've soldered 1x15 pin in, then we've pulled out the ones in the middle, and we can use our 2-pin jumper caps to make the selection that we want. In this particular case, we've selected the 3.3 volt for the VCC pin, meaning we're going to be using the onboard voltage regulator from the Arduino below that outputs a 3.3 volt. And then here we've made a D9 selection and a D7 selection. These will be very useful in our script, and we'll show that. And for the interrupt, which we're actually not using in this tutorial, it doesn't matter what you pick, but here we picked D3. So that is feature 2. Finally, we should discuss what happens if the user selects the other option here, the VR option, that is the voltage regulator option at the VCC pin. Previously we showed that the 3v3 was selected, which, as I just mentioned, takes the onboard voltage regulator from the Arduino, and so there's nothing to do other than select it, and the VCC here will be at 3.3 volt. However, if this is selected, the 3.3 output of the Arduino will not be used, and instead this interface comes into play. This interface here takes in the VN of the actual Arduino, so you can power the Arduino between 7 to 12 volt. It inputs that, and you have to add an external voltage regulator to output the 3.3 that you want here. Also here you have footprints for the smoothing capacitors at the VN and the VOut to help make the voltage smoother. As an example, what we have here, we have selected the VR option, although you can't see it in the back now. We have a voltage regulator here, and also we have the 2 smoothing capacitors. One final thing about the footprint of the voltage regulator is that there are 6 different permutations that a voltage regulator could have in terms of the pin outs. This one here has VN, VOut, and ground. But you may have a voltage regulator that has ground in the middle, so you can simply move the voltage regulator 1 over, and then everything will be aligned. So please do check the data sheet of your voltage regulator and the pin outs, and you are sure to find one combination that will fit here. Feature number 3 is regarding this section of the board here. This is the I2C interface. There's 3 I2C interfaces here, 1, 2, and 3 as marked. Number 1 and 2 would easily be accessible if a 2x4 female header is soldered into this, and you can simply plug into the corresponding through holes. Interface number 3 is designed for a standard 4-pin screw terminal. We also have the pull-up resistors here for the SCL and the SDA line. Note that there's footprints for both the through holes resistor, but also a 0805 package for the SMD resistors. The same footprint is on the back of this as well, so you could in theory add them in parallel. So let's take a look at an example that we will be seeing later. Here we have added the 4-pin screw terminal, and we simply put in the DuPont wires into our LCD, and that is it. We did not need to add any pull-up resistors in this case. It was not necessary, but if your project requires it, then you have the option to do so. And we have still another 2 I2C interfaces available for anything else that we may want. Feature number 4 is regarding this section of the board right here. This is the SPI interface. The SPI interface also has a selection pin right here, which is a 1x3. So here, to do this, you can either simply use a 1x3 male header, or you can see that these are teardrop shaped solder pads. It's very easy to cross that bridge with a little bit of solder, which is the same as the other one. Actually, I didn't mention before. Anyways, the SPI here has only one option, and that's for the chip select pin, and it's the option D10 and D9. Note that that is a repeat of the chip select pin that we discussed previously. So why do we want the SPI pin output here? Number 1, it's great for if you want to attach an oscilloscope and see the output for the SPI. So if you've selected, say, D10 here, you can also select D10 here, and you're going to see the output of the RF module. If you have something else that you want to see, then keep D10 here, but select D9, and then adjust your script accordingly. So it's a nice little output to have. Feature number 5 is a very simple breakout section here, prototyping section. There's not a lot of pins, but the V5 and the ground are already taken out, marked here, and we also have D6, D5, and A0 available. So you could, for example, put an LED or 2 here that would do something when a signal, for example, comes in. So it's not a lot of space, but if you utilize it well, you can put a couple LEDs or a buzzer or some other way to interface here. Feature number 6 is regarding the stackability of the shield. The NRF-Shield is fully stackable in the sense that if you were to use stacking headers instead of these standard headers, you can bring up all of the pins from the layer below. Also, if you were to use the NRF Mini, this guy, then the height of the shield would be small enough that it would fit inside of a stack. That being said, we don't recommend that this shield is in the middle of a stack, but rather be on top, for the simple reason that the RF communication works best when the antenna is not obstructed. We note that on this bottom row of headers, there is also an empty, unplated, unmarked through hole. So in the same way that we used the trick here to make a long 1x15 pin header, we can do the exact same thing here, and afterwards just pull this pin out. So then it'll look just like this. This makes soldering just a little bit easier. The other side it doesn't work because the spacing here is not a full space, but rather half space. So that is the last feature, feature number 6. So now that we discussed the features of the NRF-Shield, let's actually get to the tutorial and finish it up. What you're looking at here is the sender node. The sender node is very simple. All we've done is soldered in a 2x4 female header. Let's take this guy off. We soldered in a 2x4 female header. Then we soldered in a 1x15 male header here. That's it. Well, of course you still need your headers here for connecting to the board. So there's not a lot to do. In terms of selecting the pins, we've chosen the 3v3, the D9, the D7, and the D3. We've already discussed at length what this does. The D9 and the D7 selection will be very useful in the script. We'll overlay a script image that shows where these are used, and again we're going to have the full script available for download below. Also the interrupt pin, as mentioned already, we are not using. So that is it. Note also we're using the Arduino Mega to interface. As mentioned, the NRF-Shield is compatible with the Uno R3, the Mega, the Leonardo, the Due, and any other microcontroller. Doesn't have to be Arduino, any other microcontroller that has a similar pinout. So let's talk about the receiver. The receiver has all of the same soldering joints as the sender, so reproduce the exact same thing. But there's also additional things that the user needs to do. Number one is we're using the long or the large NRF module, and as said before, we need to have these supporting female headers. Technically they're not used, these are just grounded, but they add a lot of stability to this module. So if we put it back in, you can see that it nicely supports this module here, and it makes it a lot stronger. By the way, you might be asking, why don't we just solder these modules directly into the NRF-Shield? Why are we using male and female headers? Simply being, I like to recycle these components. I like to use them in different projects, and if one of these components breaks, it's very easy just to change it out. That's a standard practice I do with a lot of things. Things that are low cost, or I have many of, or anything along those lines, I solder directly in, such as these components here. But any module or anything else that's something like this, I typically do that. So that is this. Notice also we have selected the VR pin here, and we have selected the, it's hard to tell, but it is the D10 pin, the D8 pin, and the D2. These two pins, again, will overlay an image of the script where that is used, and interrupt we're not using. Now, because we're using the VR, as said before, we also added the voltage regulator and the two smoothing capacitors. Finally, to output the data, we added a 4-pin screw terminal and connected it directly to an LCD module. This LCD module, very common, a lot of you will have it and have lots of experience with it, communicates with the Arduino via I2C bus because of this I2C backpack that's attached. A lot of the LCDs have this, and make sure that yours does too. Otherwise, you can't connect with just 4 pins, you'll need a lot more pins. So you could see the flexibility having done all this with the selection pins. For example, if in a future project you want to recycle this NRF-Shield, you don't want to use up another one, you can change the selection pins that match your particular project at that time. You may not want to use the voltage regulator for the other project. In this project, on the receiver node, I want to. This larger module can use up more currents, and to ensure a stable communication is established, we use an external voltage regulator. But also, in a different project, we may want to switch up these pins depending if there's more shields in the stack that already use up these pins. Same with the interrupt as well. You can see that there's still more room for making this project more comprehensive and more flexible. We have not used the other two I2C interfaces, we have not used the SPI interface, and we also still have the prototyping breakout section here. So hopefully this tutorial has been useful, and that is shown the flexibility of the NRF-Shield and how to easily get going and get your first project with the NRF-Shield off the ground.